Theorem 1.4. Prove that root 2 is irrational. Okay. Let us assume to the contrary that root 2 is a rational number. Okay. Now, if a number is said to be a rational number, then it can be represented in the form of P by Q. So, hence root 2 can be represented as R by S, where S not is equal to 0. Okay. Now, if there is any other common factors other than 1 for R and S, we have to divide R and S with that common factors, so that we get root 2 is equal to A by B, where A and B are said to be co-primes. That is, if A and B are said to be co-primes, that is, there is no other common factor other than 1. Okay. Now, from this equation, root 2 is equal to A by B, A is equal to root 2 into B. Squaring on both sides, we get A square is equal to 2 into B square. Here, if you observe this equation from theorem 1.3, it states that if A square is divided by 2, then A can also be divided by that prime number P, and P is one of the factor of A square. So, here if A square is divided by the prime number 2, hence A can also be divided by 2 with the help of the theorem 1.3, and 2 is one of the factor for A square. Okay. Now, let us consider the value of A is equal to 2c for some value of integer c. Then, if we substitute the value of A is equal to 2c in this equation, we get 2b square is equal to 4c square. From this, b square is equal to 2 into c square. Again, from this equation, by using theorem 1.3, if b square is divided by any prime number p, then b also divided by with the prime number p, and p is one of the factor for b square. That is, here the prime factor p is 2, b square is divided by 2, then b also divided by 2, and 2 is the factor of b square. Now, by observing these two cases, we came to conclusion that for A square and B square, we are having a common factor, that is 2. This contradicts the fact that A and B have no common factor other than 1. But here it is completely quite opposite. These two having a common factor of 2. This is why, because this contradiction has arisen because of our incorrect assumption that root 2 is rational. Hence, we conclude that root 2 is an irrational number. Example 9. Prove that root 3 is irrational. Okay. Let us assume to the contrary that root 3 is a rational number. If a number is said to be a rational number, we can write in the form of P by Q. So, I can write root 3 is equal to R by S, where S is not equal to 0. Okay. Now, if there is any common factors other than 1 for R and S, then we have to divide R and S with that common factors. Then we get root 3 is equal to A by B, where A and B are said to be co-primes. That is, if when we say A and B are said to be co-primes, then there is no common factor for A and B other than 1. Okay. Now, from this equation, root 3 is equal to A by B, A is equal to B into root 3. Squaring on both sides, we get A square is equal to B square into 3. So, here from the theorem 1.3, if A square divided by any prime number P, then A can also be divided by that prime number P, and prime number P is one of the factor of A. So, here 3 is dividing the A square, hence from the theorem 1.3, 3 also divides A, and 3 is one of the factor of A. Okay. Now, if you consider the value of A is equal to 3c in the above equation, we get 3b square is equal to 9c square. 3b square is equal to 9c square. So, from that b square is equal to 3 into c square. So, again from the theorem 1.3, it clearly says that if b square divided by any prime number p, then b also divided with that prime number p, and p is one of the factor of b. Hence, here b square is divided by 3, and now by theorem 1.3, b also divided by 3, and 3 3 is one of the factor of b. So from these two equations we came to a conclusion that these two, a and b, have a common factor of 3. But this contradiction, the fact that a and b have no common factors other than y. Why? Because in the above statement we treated that a and b are said to be co-prime, but here we are getting a and b as 3 as a common. So this contradiction has arisen. Why? Because we are treating root 3 is a rational number. So we conclude that root 3 is an irrational number. Example 10. Show that 5 minus root 3 is irrational. Okay. Let us assume to the contrary that 5 minus root 3 is a rational number. So if a number is said to be a rational number, then we can write it in the form of p by q. So I can write 5 minus root 3 is equal to r by s, where s not equal to 0. Let us consider r and s have some common factors other than 1. Then we have to divide r and s with that common factors, so that 5 minus root 3 becomes 5 minus root 3 is equal to a by b, where a and b are said to be co-primes. Okay. Now from this equation 5 minus root 3 is equal to a by b, root 3 is equal to 5 minus a by b. Here these terms 5, a and b are said to be integers. That is, if you want to substitute any values of a and b in the above equation, we get root 3 is a rational number. But in the previous classes we proved that root 3 is irrational number. This contradicts the fact that root 3 is irrational, but this contradiction has arisen. Why? Because of our incorrect assumption that 5 minus root 3 is a rational number. So hence we conclude that 5 minus root 3 is irrational number. Note, see, the sum or difference of a rational number with an irrational number is always irrational. Example 11. Show that 3 root 2 is irrational. Okay, let us assume to the contrary that 3 root 2 is a rational number. Now, if a number is said to be a rational number, then we can write it in the form of a p by q. So 3 root 2 can be written as 3 root 2 is equal to r by s, where s not equal to 0. If let us consider r and s have some common factors other than 1, then we have to divide r and s with that common factors, so that we get 3 root 2 is equal to a by b, where a and b are said to be co-primes. Okay. Now from this equation root 2 is equal to a by 3b. Here when you observe a, 3 and b, all these are integers. That is, if you substitute any value of a and b in the above equation, we are getting root 2 is rational. This contradicts the fact that root 2 is irrational. We already proved in the previous videos that root 2 is an irrational number, but here we are getting root 2 as a rational number when we substitute any values of a and b. So this contradiction has arisen because of our incorrect assumption that root 2 is rational. Hence we conclude that 3 root 2 is irrational. Okay. Note, the product or the difference of a non-zero rational number and irrational number is always irrational. In the above problem, what we have said, the sum or product of a rational number with irrational number is always irrational. Note 2, the product and quotient, that is division, the product and division of a non-zero rational number and irrational number is always irrational. Okay, these two notes are kept in mind so that it can help in solving further problems, right? Okay.